Hello there, and welcome to the Drowsy Inquirer. I'm so glad you're here tonight because we're about to drift toward the most mysterious objects the universe has ever created. Tonight, we're exploring black holes. Wherever you are right now, let this be your moment to let go. Let the weight of the day settle. Let your muscles soften. Let your thoughts slow to a pace that feels like breathing, steady and unhurried, requiring nothing from you at all. Black holes are often spoken of with fear or spectacle, as cosmic monsters that devour stars and swallow light. But tonight, we are not here for spectacle. We are here for wonder, because black holes, for all their strangeness, are among the most elegant objects in the universe. They are places where the deepest laws of physics are stretched to their limits, and where time bends so far that it nearly stops, and where the boundary between something and nothing becomes impossibly thin. Tonight we will begin at the edge, where light still escapes and moves slowly inward. We will learn what a black hole actually is, how one forms from the death of a star, and what happens to space and time near its border. We will see the first photograph ever taken of a black hole's shadow, meet the silent giant at the center of our own galaxy, and sit with questions that even the greatest physicists alive cannot yet answer. Some of what you hear may surprise you. Some may quietly rearrange the way you think about darkness, about gravity, about what it means for something to be truly invisible. And some may simply drift past, soft and unhurried as you settle deeper into rest. If this kind of peaceful curiosity brings you comfort, consider leaving a like or subscribing. It helps other quiet minds find their way here too, one sleepy night at a time. But for now, let your body grow heavy. Let your breath find its own rhythm. And let's begin this slow journey into the deepest dark the universe has to offer. A black hole is not a hole at all. The name is misleading. When you hear black hole, you might imagine an opening in space, a pit or a tunnel leading somewhere else. But a black hole is not a hole in anything. It is an object, an extraordinarily dense, extraordinarily compact object, with gravity so intense that nothing, not even light, can escape from its vicinity once it gets too close. A black hole forms when a massive amount of matter is compressed into a very small space. Thus, the resulting gravitational field becomes so strong that the escape velocity, the speed you would need to break free, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Not a rocket, not a radio signal, not a single photon. From the outside, a black hole is invisible in the truest sense. It does not glow. It does not reflect. It produces no signal of any kind from within its boundary. It is detectable only through the effects it has on the things around it, the bending of light, the motion of nearby stars, the superheated glow of gas spiraling toward it. But despite its invisibility, a black hole is not nothing. It has mass, it has spin, it has a measurable effect on everything around it. It is one of the most substantial things in the universe, hiding behind a veil of absolute darkness. Not a hole, but a presence. Not an absence, but the deepest kind of fullness, wrapped in shadow. Every object has an escape velocity, and for black holes, it exceeds the fastest speed possible. To understand why nothing escapes a black hole, it helps to understand the idea of escape velocity. Every object with mass has one. It is the minimum speed something must reach to break free of that object's gravitational pull without any further propulsion. For the Earth, the escape velocity is about 11.2 kilometers per second. A rocket leaving Earth must reach at least that speed to avoid falling back. For the Sun, the escape velocity at its surface is about 617 kilometers per second. For a white dwarf, it is higher still. And for a neutron star, it reaches roughly 100,000 kilometers per second, or about a third of the speed of light. Now imagine compressing more and more mass into a smaller and smaller space. The escape velocity climbs. At some point, It reaches 300,000 kilometers per second, the speed of light. And at that point, something fundamental changes. Since the speed of light is the absolute maximum speed in the universe, nothing can go fast enough to escape. Not matter, not energy, not information. That threshold is what defines a black hole. It is the point where gravity wins completely, where the curvature of space-time becomes so steep that every possible path, even the path of a beam of light, curves back inward. There is no direction you can point that leads away. Every road leads to the center. The event horizon is a boundary you can cross, but never return from. Surrounding every black hole is an invisible border called the event horizon. It is not a surface. You cannot touch it. It is not made of anything. It is simply the mathematical boundary beyond which the escape velocity exceeds the speed of light. Cross it and you are committed. There is no turning back, no signal you can send, no force that can pull you out. The name Event Horizon is carefully chosen. It marks the horizon of events, the limit beyond which events can no longer be observed from the outside. Anything that happens inside the event horizon is permanently hidden from the rest of the universe. Light emitted inside cannot reach an outside observer. Signals cannot escape. Information is locked away. For a black hole with the mass of the sun, the event horizon would be a sphere about 6 kilometers in diameter. For a black hole with 10 solar masses, about 60 kilometers. For the supermassive black hole at the center of the Milky Way, with 4 million solar masses, the event horizon spans roughly 24 million kilometers, about 17% of the distance from Earth to the Sun. The event horizon is not dangerous in itself. If the black hole is large enough, you could cross it without feeling anything unusual. There is no wall, no flash, no alarm. Locally, space seems perfectly normal. But from the moment you cross, every trajectory available to you, forward, backward, sideways, upward, all of them lead to the singularity at the center. You have not entered a prison. You have entered a future from which there is no escape. At the center of a black hole, everything we know about physics stops working. Deep inside the event horizon, at the very heart of a black hole, lies the singularity. It is the point where the mathematics of general relativity predicts that the curvature of space-time becomes infinite. Density becomes infinite. Volume becomes zero. The neat, reliable equations that describe the rest of the universe produce answers that are no longer meaningful. This is not just an extreme. It is a breakdown. The singularity is not a place we do not understand well. It is a place where our best theories stop making sense entirely. General relativity, which describes gravity and the large-scale structure of the universe with extraordinary precision, simply fails here. The numbers become infinite, and infinities in physics are usually a sign that something is missing from the theory. Most physicists believe that a complete theory of quantum gravity, one that successfully combines general relativity with quantum mechanics, would resolve the singularity. Perhaps the matter does not truly collapse to a point. Perhaps quantum effects create a minimum size, a floor below which further compression is impossible. Perhaps the singularity is replaced by something else entirely, something that our current mathematics cannot yet describe. For now, the singularity remains a mystery inside a mystery, a place hidden behind the event horizon, unreachable by observation and unexplainable by existing theory. It is the universe's deepest secret, sealed behind a door that no light can open. If you fell into a large black hole, you might not even notice. This is one of the most counterintuitive facts about black holes. Yet you might expect that crossing the event horizon would be dramatic, a flash of light, a wall of force, some unmistakable sign that you have passed the point of no return. But for a sufficiently large black hole, the crossing would be entirely uneventful. The reason lies in the size of the event horizon. For a supermassive black hole with billions of solar masses, The event horizon can be larger than the entire solar system. At that scale, the curvature of space-time at the horizon is very gentle. There are no extreme tidal forces, no sudden changes in the local physics. An astronaut crossing the event horizon of such a black hole would notice nothing unusual at all. Space would seem flat, time would seem normal. The stars behind would still be visible. The drama is not in the crossing, it is in what comes after. Once inside, every trajectory curves inward. No matter which direction you try to move, you are drawn closer to the singularity. Time itself, inside the event horizon, conspires against you. The singularity is not a place in space you can avoid. It is a moment in time that you will inevitably reach, just as you will inevitably reach tomorrow. But in those final moments, if the black hole is large enough, the universe outside would remain visible. You could look up and see stars, distorted and blue-shifted, compressed into a shrinking circle of light above you. The last thing you would see, before physics as we know it fails, is the universe looking back at you. Black holes do not suck everything in. One of the most persistent misconceptions about black holes is that they are cosmic vacuum cleaners, pulling everything nearby into their maw. But this is not how gravity works. A black hole's gravitational pull at a given distance is no stronger than that of any other object with the same mass. If the sun were suddenly replaced by a black hole of equal mass, the Earth would not be sucked in. It would continue orbiting exactly as it does now, following the same path, at the same speed, in the same direction. The only difference would be the absence of sunlight. The gravitational field at Earth's distance would be identical because the mass has not changed, only its distribution. Black holes are dangerous only to things that venture very close. Gas, dust, and even stars that pass near the event horizon can be captured and pulled in. But objects at a safe distance orbit peacefully, just as planets orbit stars and moons orbit planets. In fact, when the supermassive black hole at the center of our galaxy, Sagittarius A star, is surrounded by thousands of stars that have been orbiting it for millions of years without incident. They circle it at tremendous speeds, held in orbit by its gravity, but never falling in. The black hole is not hunting them. It is simply there, massive and patient. And the stars dance around it like fireflies around a lantern that emits no light. Black holes come in a remarkable range of sizes. Not all black holes are alike. They span an astonishing range of masses, from modest remnants of dead stars to titans that anchor entire galaxies. And the differences between them are not just numerical. They shape the behavior, the appearance, and the fate of everything around them. The smallest confirmed black holes are stellar mass black holes, formed from the collapse of massive stars. These typically range from about 5 to a few tens of solar masses. Their event horizons are measured in kilometers, small enough to fit inside a city. At the other extreme are supermassive black holes, which contain millions to billions of solar masses. These giants sit at the centers of most large galaxies, including our own. Their event horizons can span millions of kilometers, larger than the orbit of Mercury around the Sun. Between these two categories lies a puzzling middle ground. Intermediate mass black holes, with masses ranging from hundreds to hundreds of thousands of solar masses, have been harder to find. A few candidates have been identified, but their formation mechanism remains unclear. They may represent a missing link in the evolution of black holes. They're bridging the gap between the death of a single star and the birth of a galactic anchor. And there may be even smaller black holes. Theoretical primordial black holes, formed in the extreme conditions of the early universe, could have masses as small as an asteroid or even less. None have been detected, but the search continues. The universe may be hiding black holes at scales we have not yet learned to see. Some stars end their lives in the most violent events in the cosmos. The story of a stellar mass black hole begins long before the black hole itself. It begins with a star, a very massive star, one born with at least 20 to 25 times the mass of the Sun. These stars live fast. They burn through their nuclear fuel in just a few million years, a blink compared to the Sun's 10 billion-year lifespan. During its life, such a star fuses hydrogen into helium, then helium into carbon, then carbon into neon, oxygen, silicon, and finally iron. Each stage produces less energy and lasts a shorter time. The star is racing toward its own end, and it does not know how to stop. Iron is the terminus. Unlike all the elements before it, iron fusion does not release energy. It consumes it. When the core becomes iron, the engine that has supported the star against its own gravity for millions of years suddenly shuts off. In less than a second, the core collapses. The outer layers, no longer supported, come crashing inward at speeds up to 70,000 kilometers per second. The result is a supernova, one of the most energetic events in the universe. The outer layers are blown outward in a shock wave that can briefly outshine an entire galaxy. And at the center, depending on the mass of the collapsing core, what remains is either a neutron star or a black hole. If the core exceeds roughly 2 to 3 solar masses, not even the pressure of neutrons can resist the crush of gravity, and the core collapses beyond all known states of matter, forming a black hole. A star that once shone across light years of space becomes a region of space-time from which no light will ever emerge again. A 19-year-old on a ship calculated the destiny of dying stars. In 1930, a young Indian physicist named Subramanian Chandrasekhar boarded a ship from Madras to Cambridge, England. During the 18-day voyage, he worked on a problem that had been nagging at him. What is the maximum mass a white dwarf star can have before it can no longer support itself against gravitational collapse? White dwarfs are the remnants of ordinary stars like the Sun. When such a star exhausts its fuel, its core contracts and is supported by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being squeezed too close together. But Chandrasekhar realized that this pressure has a limit. Using special relativity and quantum mechanics, he calculated that a white dwarf with a mass greater than about 1.4 times the mass of the Sun could not sustain itself. Above this threshold, now called the Chandrasekhar limit, the white dwarf would collapse further, potentially becoming a neutron star, or, if massive enough, a black hole. His result was initially met with skepticism, even ridicule, from some of the most prominent astrophysicists of the day. Arthur Eddington, one of the most respected scientists in the world, publicly dismissed the idea, arguing that nature would not allow such a collapse. But Chandrasekhar was right. Decades of observations have confirmed his limit again and again. He received the Nobel Prize in Physics in 1983, more than 50 years after that ship voyage. A teenager with a pencil and a notebook, sailing across the Indian Ocean, had calculated one of the most important numbers in the life and death of stars. Neutron stars are the alternative to total collapse. When a massive star's core collapses in a supernova, but the remaining mass is below a certain threshold, roughly 2 to 3 solar masses, the result is not a black hole. It is a neutron star, one of the most extraordinary objects in the universe. A neutron star is what happens when matter is compressed beyond the point where even atoms can maintain their structure. Electrons are forced into protons, creating neutrons. The entire core becomes a single enormous ball of neutrons, roughly 20 kilometers across, but containing more mass than the Sun. The density is almost beyond comprehension. A single teaspoon of neutron star material would weigh about 6 billion tons on Earth. That is roughly the weight of a mountain compressed into a volume smaller than a sugar cube. If you could somehow stand on the surface of a neutron star, The gravity would be about 2 billion times stronger than the gravity on Earth. Neutron stars are supported against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed any further. But this resistance, like the electron degeneracy pressure in white dwarfs, has a limit. If the mass exceeds that limit, not even neutrons can hold the line, and the collapse continues. The object crosses the threshold from extraordinary density to infinite density, from neutron star to black hole. The boundary between the two is narrow. Just a fraction of a solar mass can make the difference between a star that becomes one of the densest stable objects in the universe and one that becomes a region of space-time from which nothing returns. A supernova can briefly outshine its entire galaxy. When a massive star finally collapses and its outer layers are blown outward, the resulting explosion is one of the most luminous events in the known universe. A single supernova can, for a few weeks, radiate more energy than all the billions of stars in its host galaxy combined. The energy released in a supernova is staggering. In just 10 seconds, the collapsing core emits more energy in the form of neutrinos than the sun will produce in its entire 10 billion-year lifetime. The visible light from the explosion, the part we can actually see, represents only a tiny fraction of the total energy budget. Supernovae have been observed by humans throughout history. In 1054, Chinese and Japanese astronomers recorded a guest star so bright it was visible during the day for weeks. The remnant of that explosion is now the Crab Nebula. In 1572, Tycho Brahe observed a supernova that challenged the prevailing belief that the heavens were unchanging. And in 1987, a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, each became the closest observed supernova in nearly 4 centuries. Each supernova scatters heavy elements, carbon, oxygen, iron, gold, into space. These elements mix with interstellar gas and eventually become part of new stars, new planets, and new life. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it was forged in the cores of massive stars and scattered by supernova billions of years ago. The death of a star is not an ending. It is a distribution, a giving back, a seeding of the cosmos with the ingredients for everything that will come next. The largest black holes may not have formed from dying stars at all. At the centers of most large galaxies sit black holes of almost unimaginable mass, millions to billions of times the mass of the Sun. These are the supermassive black holes, and their existence raises a difficult question. How did they get so big? If they grew from stellar mass black holes, they would have needed to consume enormous amounts of matter over billions of years. But observations of very distant quasars, powered by supermassive black holes, show that some of these giants were already in place less than 1 billion years after the Big Bang. There simply was not enough time for them to grow from small seeds by normal accretion. This has led to alternative theories. One possibility is direct collapse. In the early universe, enormous clouds of pristine gas, uncontaminated by heavy elements, may have collapsed directly into black holes without first forming stars. These direct collapse black holes could have been born with masses of tens of thousands or even hundreds of thousands of solar masses, and giving them a significant head start. Another possibility involves the rapid merging of smaller black holes and dense star clusters in the crowded environment of the early universe, building mass quickly through collision after collision. And some models suggest that the seeds of supermassive black holes may have formed from exotic processes in the very first moments after the Big Bang. The truth is, we do not yet know exactly how the largest black holes formed. They are among the oldest and most massive objects in the cosmos, and their origins remain one of the great unsolved puzzles in astrophysics. The Big Bang itself may have created tiny black holes. Most black holes we know about form from the deaths of stars, but there is a theoretical category that may have formed much earlier, in the first fractions of a second after the Big Bang. These are called primordial black holes, and they are among the most intriguing hypothetical objects in physics. In the extremely hot, dense conditions of the early universe, small regions of space may have had slightly higher density than their surroundings. If those density fluctuations were large enough, they could have collapsed under their own gravity before the universe had time to expand and dilute them. The result would be black holes with a wide range of masses, from less than a gram to thousands of solar masses. Primordial black holes with very small masses would have evaporated long ago through Hawking radiation. But those with masses comparable to asteroids or small planets could still exist today, drifting unseen through the cosmos. Some physicists have even proposed that primordial black holes could account for some or all of the universe's dark matter, the mysterious invisible mass that outweighs all visible matter by roughly 5 to 1. No primordial black hole has ever been detected, but the search is active, using gravitational lensing surveys, gamma-ray observations, and gravitational wave detectors. If they are found, they would open a window into the conditions of the universe in its earliest moments, a time before any star had formed, before any light had been released, when the cosmos was still deciding what it would become. When two black holes collide, they shake the fabric of the universe. Imagine two black holes, each with the mass of dozens of suns, spiraling toward each other across millions of years. As they draw closer, they orbit faster. The space between them shrinks, and in the final moments before they merge, they are circling each other hundreds of times per second, moving at a significant fraction of the speed of light. When they finally touch, they do not collide the way solid objects do. They merge. Their event horizons combine. Their singularities hidden inside become one. And in that merger, an enormous amount of energy is released, not as light, but as gravitational waves, ripples in the fabric of space-time itself. These ripples spread outward at the speed of light, stretching and compressing space as they pass. By the time they reach Earth, they are extraordinarily faint, changing the distance between 2 points by less than 1,000th of the diameter of a proton. But on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected exactly this kind of signal for the first time. The event, designated GW150914, was the merger of two black holes roughly 36 and 29 solar masses, about 1.3 billion light-years away. In less than a second, the merged black hole radiated away about 3 solar masses of energy as gravitational waves, more energy than all the stars in the observable universe were emitting in light at that moment. Einstein had predicted gravitational waves a century earlier, in 1916. He was not sure they were real. He even tried to retract the prediction, but they were real. And for the first time, humanity could hear the universe not through light, but through the vibrations of space-time itself. Time slows to a crawl near a black hole. One of the most profound consequences of general relativity is that gravity affects the flow of time. The stronger the gravitational field, the slower time passes. Near a black hole, this effect becomes extreme. Imagine two observers. One remains far away from the black hole, in open space where gravity is weak. The other slowly descends toward the event horizon. As the descending observer moves closer, time for them, relative to the distant observer, begins to slow. A clock strapped to their wrist would tick more and more slowly as seen from the outside. At first, the difference is negligible, but as the observer approaches the event horizon, the time dilation becomes dramatic. Minutes for the falling observer correspond to hours for the distant one. Hours become years. And at the event horizon itself, from the perspective of the distant observer, time appears to stop entirely. This does not mean the falling observer experiences frozen time. From their own perspective, everything feels normal. Their heart beats at the same rate. Their thoughts flow as usual. They cross the event horizon and continue falling, unaware that anything special has happened. But from the outside, they appear to slow down, redden, and fade, never quite reaching the boundary, stretching out like an image reflected in a darkening mirror. This is not a trick of observation. It is a real physical effect. Time genuinely flows at different rates depending on the strength of the gravitational field. And near a black hole, the difference becomes so extreme that the very concept of simultaneity, the idea that two events can happen at the same time, loses its meaning. To an outside observer, you would freeze at the edge forever. If you were watching someone fall toward a black hole from a safe distance, you would see something haunting. As they approach the event horizon, their image would slow down. Their movements would become sluggish. The light they emitted or reflected would be stretched to longer and longer wavelengths, shifting from visible light to infrared to radio waves. They would appear to redden, growing dimmer with each passing moment. Their image would flatten against the event horizon, becoming a ghostly silhouette that fades but never quite disappears. From your perspective, they would never cross the boundary. They would remain there, frozen in time, growing darker and dimmer over an eternity. This is not an illusion. It is a direct consequence of the way light escapes, or fails to escape, from the curved space-time near a black hole. Photons emitted closer to the event horizon have to climb out of a deeper gravitational well. They lose energy in the process, their wavelengths stretching. At the horizon itself, the photon would need infinite energy to escape, so it never does. The falling observer, meanwhile, experiences none of this. They cross the horizon in finite time by their own clock, oblivious to the fact that from the outside, their image has become an eternal, fading ghost. Two realities, both true, separated by the warping of space-time. It is one of the strangest consequences of general relativity. The same event, crossing the event horizon, looks completely different depending on where you stand, and both views are equally valid. Near a small black hole, a gravity would stretch you like a strand of pasta. If you were unfortunate enough to fall toward a stellar mass black hole, one with perhaps 10 times the mass of the Sun, you would encounter a force that physicists have given a surprisingly playful name: spaghettification. The tidal force near a black hole is the difference in gravitational pull between 2 points separated by a small distance. Near a compact object, gravity is significantly stronger at a point closer to the center than at a point slightly farther away. For a stellar mass black hole, this difference becomes extreme well before you reach the event horizon. If you were falling feet first, the gravity at your feet would be measurably stronger than the gravity at your head. This difference would stretch your body vertically while compressing it horizontally. And as you got closer, the stretching would intensify. Your body would be pulled into a long, thin strand, like a piece of spaghetti being drawn through the curved geometry of space-time. This process is not instantaneous. It begins gradually and accelerates. Long before you reach the singularity, you would have been reduced to a stream of individual atoms, stretched into a thin filament spiraling inward. It sounds violent, and it is. But it is worth noting that spaghettification is significant mainly for smaller black holes. For a supermassive black hole, the event horizon is so far from the singularity that the tidal forces at the boundary are remarkably gentle. You could cross the event horizon of a billion solar mass black hole and feel less tidal force than you feel from the moon on Earth right now. The danger comes later, to deeper inside, where the curvature steepens and the stretching begins. But at the threshold, the giant is gentle. Near the event horizon, light itself can orbit the black hole. Just outside the event horizon of a non-rotating black hole, At a distance of 1.5 times the Schwarzschild radius, there exists a remarkable region called the photon sphere. At this precise distance, the curvature of space-time is such that photons, particles of light, can travel in circular orbits around the black hole. This means that if you were standing at the photon sphere and looked straight ahead along the tangent, you would, in principle, see the back of your own head. Light leaving the back of your skull would travel all the way around the black hole and return to your eyes. Of course, the orbit is unstable. The slightest perturbation would send the photon either spiraling inward toward the event horizon or escaping outward into space. But for one perfect fleeting moment, light traces a circle around the darkness. The photon sphere is one of the most elegant predictions of general relativity. It is the boundary between light that can still escape and light that is too close to ever leave. Photons that pass just outside this boundary are deflected, but eventually continue on their way. Photons that pass just inside are captured, spiraling inward until they cross the event horizon. When the Event Horizon Telescope captured the first image of a black hole in 2019, the bright ring in the photograph was closely related to the photon sphere. The light forming that ring came from photons that orbited the black hole one or more times before escaping toward Earth, carrying with them a portrait of the most extreme gravitational environment we can observe. Spinning black holes drag space itself along with them. Most black holes are not stationary, they spin. And when a black hole spins, it does not just rotate within space, it drags space along with it. This effect, predicted by general relativity and called frame dragging, creates a region outside the event horizon known as the ergosphere. Within the ergosphere, space-time is twisted so dramatically that it is physically impossible to remain stationary. No matter how powerful your engines, no matter which direction you point your thrust, you are forced to rotate in the direction the black hole spins. Space itself is moving, and you are carried along with it, like a swimmer caught in a current too strong to resist. The ergosphere is not inside the event horizon. You can enter it and leave again. But while you are inside, you are compelled to move, dragged by the rotation of space-time itself. This is not gravity pulling you inward. It is the very fabric of the universe spinning around the black hole and taking everything with it. The existence of the ergosphere leads to one of the more remarkable theoretical possibilities in black hole physics. In 1969, the mathematician Roger Penrose proposed a process by which energy could be extracted from a spinning black hole. If an object enters the ergosphere and splits into two pieces, one piece falling into the black hole and the other escaping, the escaping piece can carry away more energy than the original object had. The energy comes from the black hole's rotation, slowing it down slightly. This is not science fiction. It is a mathematically rigorous consequence of general relativity. A spinning black hole is, in a sense, a reservoir of rotational energy, and the Penrose process is the key that could, in principle, unlock it. Inside a black hole, space and time trade places. This is one of the most disorienting truths in all of physics. Outside a black hole, you can move freely in any spatial direction, forward, backward, left, right, up, down, but you cannot move freely in time. Time flows in one direction, always forward, carrying you relentlessly toward the future. You can choose where to go, but you cannot choose when. Inside the event horizon, this relationship reverses. The radial coordinate, the one that measures distance from the singularity, takes on the mathematical properties of time, and time takes on the properties of space. What this means in practical terms is that moving toward the singularity is no longer a matter of direction, it is a matter of time. You cannot avoid the singularity any more than you can avoid tomorrow. It is not a place ahead of you. It is a moment ahead of you, an inevitable point in your future. No matter which direction you try to move, no matter how powerful your engines, no matter what clever trajectory you attempt, All paths inside the event horizon lead to the singularity. It is not pulling you. It is waiting for you, the way the future always waits, patient and unavoidable. This swapping of space and time is not a metaphor. It is a precise mathematical consequence of the Schwarzschild solution to Einstein's field equations. Inside the event horizon, the geometry of space-time is so warped that the very meaning of movement changes. The singularity is not a destination. It is a destiny. You cannot see a black hole, but you can see what it does to everything around it. A black hole, by definition, emits no light. It reflects no light. It is the darkest object in the universe. And yet, paradoxically, the regions around black holes can be among the brightest and most dramatic environments in the cosmos. The key is the matter that surrounds them. When gas, dust, or stellar material falls toward a black hole, it does not simply drop straight in. Conservation of angular momentum causes it to spiral inward, forming a flattened rotating structure called an accretion disk. Within this disk, the material closest to the black hole moves at tremendous speeds, sometimes approaching a significant fraction of the speed of light. As particles in the disk collide and rub against each other, friction converts their kinetic energy into heat. The inner regions of an accretion disk can reach temperatures of millions or even billions of degrees, far hotter than the surface of any star. At these temperatures, the disk radiates intensely across the electromagnetic spectrum, from radio waves to visible light to X-rays. The accretion disk is the black hole's calling card. It is the glow of matter being consumed, a final blaze of energy before the material crosses the event horizon and disappears forever. It is how astronomers first identify black hole candidates, by detecting the telltale X-ray emission from superheated gas spiraling into an invisible point of overwhelming gravity. The brightest accretion disks in the universe outshine entire galaxies, and they are powered not by fusion, as stars are, but by gravity itself. The simple act of falling, converted through friction and compression into a radiance so intense it can be seen across billions of light years. Some black holes shoot jets of matter across galaxies. Among the most spectacular phenomena associated with black holes are the relativistic jets, narrow beams of matter and energy launched from the polar regions of some actively feeding black holes at speeds approaching the speed of light. These jets can extend for thousands, sometimes millions of light years, far beyond the boundaries of the galaxy that hosts the black hole. They are among the largest structures produced by single objects in the entire universe, thin streams of superheated plasma drilling through intergalactic space with extraordinary precision and power. The exact mechanism that produces jets is still not fully understood, but it is believed to involve the interaction of the accretion disk with the black hole's powerful magnetic field. As matter spirals inward, the magnetic field lines become twisted and compressed, channeling energy and particles outward along the axis of rotation. The result is a focused beam of plasma, accelerated to relativistic speeds and collimated by magnetic forces into a remarkably narrow stream. The energy carried by these jets is immense. They can inflate enormous bubbles of hot gas in the intergalactic medium, influence the formation of stars in neighboring galaxies, and redistribute matter and energy across scales that dwarf the galaxy itself. A single black hole, through its jets, can shape the evolution of its entire cosmic neighborhood. It is a striking paradox. An object from which nothing can escape is responsible for some of the most powerful outflows in the universe. The black hole consumes, but in consuming, it also creates, launching energy across distances that light itself takes millions of years to cross. The first photograph of a black hole's shadow was captured in 2019. For decades, black holes existed only as mathematical solutions, theoretical predictions, and indirect evidence. No one had ever seen one. Then on April 10, 2019, the Event Horizon Telescope collaboration released an image that changed everything. The image showed a glowing ring of light surrounding a dark central region, the shadow of the supermassive black hole at the center of the galaxy Messier, 87, 55 million light-years from Earth. The black hole, designated M87 star, has a mass of roughly 6.5 billion suns. Capturing this image was an extraordinary technical achievement. No single telescope on Earth could resolve such a small, distant object. Instead, the Event Horizon Telescope linked radio telescopes across 6 locations on 4 continents, from Hawaii to Spain to the South Pole, creating a virtual telescope with an effective diameter equal to the entire Earth. The technique, called Very Long Baseline Interferometry, allowed the team to achieve a resolution sharp enough to read a newspaper in New York from a cafe in Paris. The resulting data, collected over several nights in April 2017, amounted to about 5 petabytes, so much that it had to be physically shipped on hard drives rather than transmitted over the internet. It took 2 years of computational work to assemble the data into an image. And there it was, a ring of fire around a circle of absolute darkness. Not an artist's impression, not a simulation. The actual shadow of a black hole, seen for the first time in human history. Light that had been bent, lensed, and heated by 6.5 billion solar masses of gravity, forming a glowing halo around the deepest dark in the known universe. The bright ring in the image is light bent around the darkness. The glowing ring in the M87 star image is not the accretion disk seen face on. It is something more subtle and more profound. It is light that has been gravitationally lensed by the extreme curvature of space-time around the black hole. Some of the photons forming the ring were emitted by the accretion disk and then bent sharply by gravity, redirected toward Earth. Some photons orbited the black hole 1 or more times before escaping. Others were emitted from behind the black hole but bent around it by the warp geometry, reaching us from a direction opposite to their origin. The dark shadow at the center is the silhouette of the event horizon, or more precisely, the region from which no photons can escape. It is the black hole's own darkness, projected onto the bright background of its surrounding environment. The edge of the shadow corresponds closely to the photon sphere, the region where light orbits the black hole before either escaping or falling in. The asymmetry of the ring, brighter on one side than the other, is due to relativistic beaming. The side of the accretion disk moving toward us appears brighter because the photons are blue-shifted and concentrated in our direction. The side moving away appears dimmer. This lopsidedness is a direct consequence of the black hole's rotation and the motion of the material around it. At every detail in the image, the shape of the ring, its brightness profile, its asymmetry, matches the predictions of general relativity with remarkable precision. Einstein's equations, written over a century ago, predicted exactly what this black hole would look like. And the universe, when we finally looked, confirmed it. Our own galaxy hides a supermassive black hole in its heart. At the very center of the Milky Way, roughly 26,000 light-years from where you lie tonight, there is a region of intense radio emission known as Sagittarius A star. For decades, astronomers suspected that this source marked the location of a supermassive black hole. In 2022, the Event Horizon Telescope confirmed it, releasing an image of Sagittarius A star's shadow, the second direct image of a black hole ever captured. Sagittarius. A star has a mass of approximately 4 million suns. Compressed into a region smaller than the orbit of Mercury, it is far less massive than M87 star, but it is far closer, making it appear roughly the same angular size on the sky. Imaging Sagittarius A star was actually more challenging than imaging M87 star, despite being much closer. The reason is that Sagittarius A star is much smaller, and the gas around it changes configuration much more rapidly. While M87 star's appearance remains relatively stable over days, The environment around Sagittarius A star shifts on timescales of minutes. The EHT team had to develop new algorithms to account for this variability, essentially capturing a portrait of a subject that would not sit still. The result, when it came, was strikingly similar to the M87 image. A bright ring of light, slightly asymmetric, surrounding a dark central shadow. Two black holes, separated by 55 million light-years and a factor of 1,000 in mass, producing nearly identical visual signatures. General relativity does not care about size. The physics is the same, from a black hole the size of a city to one the size of a solar system. Stars dance around our galaxy's black hole at extraordinary speeds. One of the most compelling pieces of evidence for the existence of Sagittarius. A star came not from imaging the black hole itself, but from watching the stars that orbit it. For over 2 decades, 2 independent teams of astronomers track the movements of stars in the galactic center with extraordinary precision. The star known as S2 follows a highly elliptical orbit around Sagittarius A star, completing one full orbit in approximately 16 years. At its closest approach, EIDARIS-2 passes within about 17 light hours of the black hole, roughly 4 times the distance from Neptune to the Sun, and reaches a speed of approximately 7,650 kilometers per second, about 2.5% of the speed of light. By tracing the orbits of S2 and other nearby stars, astronomers were able to calculate the mass of the invisible object they orbit. The result was roughly 4 million solar masses, concentrated in a region smaller than our solar system. No known object other than a black hole could account for this much mass in this little space. The work earned Andrea Ghez and Reinhard Genzel the Nobel Prize in Physics in 2020, shared with Roger Penrose for his theoretical contributions to black hole physics. Their observations transformed Sagittarius A star from a theoretical candidate into a confirmed reality, a supermassive black hole sitting quietly at the center of our galaxy, attended by a retinue of stars that trace its invisible shape through their obedient orbits. Some black holes reveal themselves by stealing from their neighbors. Not all black holes sit at the centers of galaxies. Many stellar mass black holes exist in binary systems, paired with an ordinary star. In these systems, the black hole and the star orbit a common center of mass, held together by mutual gravity. And if they are close enough, the black hole can begin to strip material from its companion. Gas from the outer layers of the star is pulled toward the black hole by its intense gravity. This gas does not fall directly in. It spirals inward, forming an accretion disk that heats up to millions of degrees. At these temperatures, the disk emits powerful X-rays, detectable by space-based observatories. The first strong candidate for a stellar mass black hole, Cygnus X1, was identified in exactly this way. Discovered in 1964, Cygnus X1 is a powerful X-ray source in the constellation Cygnus. Observations revealed that the X-rays were coming from a compact object orbiting a blue supergiant star. The compact object's mass, estimated at roughly 21 solar masses, was far too high for it to be a neutron star. It had to be a black hole. Since then, dozens of X-ray binary systems have been identified as containing probable black holes. Each one is a quiet drama played out across space, a visible star slowly losing itself to an invisible companion, the stolen gas forming a glowing whirlpool of light around a point of absolute darkness. Nearly every large galaxy has a supermassive black hole at its center. This is one of the most remarkable patterns in the universe. Observations over the past few decades have shown that virtually every large galaxy, and many smaller ones, harbors a supermassive black hole at its center. The Milky Way has Sagittarius A star. The Andromeda Galaxy has its own central black hole, with a mass of about 100 million suns. Messier 87 has one of 6.5 billion solar masses. The correlation goes deeper. And there is a tight relationship between the mass of a galaxy's central black hole and the mass and velocity dispersion of the galaxy's central bulge. Bigger bulges host bigger black holes. This relationship, known as the M-sigma relation, suggests that the growth of the black hole and the growth of the galaxy are fundamentally linked. How this connection works is still debated. One possibility is that the black hole regulates galaxy growth through feedback. When the black hole is actively feeding, its jets and radiation can heat the surrounding gas, preventing it from cooling and forming new stars. When the feeding stops, the gas cools and stars begin to form again. The black hole acts as a thermostat, cycling between active and dormant states, shaping the galaxy around it. And another possibility is that both the galaxy and the black hole grow together through the same processes: mergers with other galaxies, inflows of intergalactic gas, and the general accumulation of matter over cosmic time. They are not so much cause and effect as they are partners, co-evolving over billions of years. Either way, the message is clear. Black holes are not incidental to galaxies. They are central to them, in every sense of the word. One of the largest known black holes defies easy comprehension. In the constellation Canis Venatici, roughly 10.4 billion light-years from Earth, lies a quasar powered by a black hole of staggering proportions. TON 618 has an estimated mass of 66 billion suns. To understand what that means, it helps to consider scale. The event horizon of TON 618 has a diameter roughly 11 times the size of our entire solar system, measured from the Sun to the orbit of Pluto and beyond. If you place this black hole where our Sun is, its event horizon would swallow every planet, every asteroid, every comet, and extend far into the Kuiper Belt. The light from TON 618 has been traveling for over 10 billion years. We are seeing it as it was when the universe was less than a quarter of its current age. Even then, it was already enormous, already blazing with the energy of an actively feeding monster at the heart of a distant galaxy. The luminosity of TON 618 is roughly 140 trillion times that of the Sun. It is one of the most luminous objects in the observable universe. It's powered entirely by the gravitational energy of matter falling into a black hole so massive that the human mind simply cannot hold its scale without reaching for metaphor. And yet, for all its enormity, TON 618 follows the same physics as every other black hole. The same equations, the same geometry, the same relationship between mass and event horizon size. General relativity does not flinch at 66 billion solar masses. It simply stretches the same elegant mathematics to a scale that leaves us quietly speechless. An even larger black hole was discovered more recently. In 2022, astronomers identified a black hole at the center of the galaxy cluster, Abell 2029, that may be even more massive than TON 618. Named Phoenix A, this black hole has an estimated mass of approximately 100 billion suns, making it one of the most massive black holes ever measured. Phoenix A sits at the center of a brightest cluster galaxy, a giant elliptical galaxy that itself sits at the heart of a large galaxy cluster. Its enormous mass has been estimated through observations of the motions of stars near the galactic center and through the dynamics of the surrounding gas. At 100 billion solar masses, Phoenix A's event horizon would span a diameter of roughly 600 billion kilometers. For comparison, light would take about 23 days to cross it. The entire solar system, from the Sun to the outermost reaches of the Oort cloud, would fit comfortably inside. The existence of such colossal black holes raises profound questions about the limits of black hole growth. Is there a maximum size? Some theoretical models suggest that there may be, because as a black hole grows, its radiation becomes so intense that it pushes away the very material it needs to feed on, a self-limiting process. But others suggest that under the right conditions, black holes can grow to almost any size. Phoenix A sits near the upper edge of what current models predict. It is a quiet monument to the power of gravity accumulated over billions of years, patient and persistent, growing 1 mil at a time until it became one of the most massive single objects in the known universe. Quasars are the brightest objects in the universe, powered by black holes. When a supermassive black hole is actively feeding, consuming large amounts of gas and dust, the accretion disks surrounding it can become extraordinarily luminous. So luminous, in fact, that it outshines the entire galaxy hosting it. These objects are called quasars, short for quasi-stellar objects, because when they were first discovered in the 1950s and 1960s, they looked like points of light, similar to stars but with properties that no star could explain. The most luminous quasars are thousands of times brighter than the Milky Way, emitting energy equivalent to trillions of suns. This energy comes not from nuclear fusion, as in stars, but from the gravitational potential energy of matter spiraling into the black hole. As material in the accretion disk loses angular momentum through friction and magnetic interactions, it falls inward, converting gravitational energy into radiation with an efficiency that can reach 40% of the rest mass energy, far more efficient than nuclear fusion, which converts less than 1%. Most quasars are found at great distances, which means we are seeing them as they were billions of years ago, when the universe was younger and black holes were feeding more actively. In the nearby universe, quasars are rare. Most supermassive black holes, including Sagittarius A star, are in a quiescent state, with very low accretion rates and correspondingly dim surroundings. Quasars serve as beacons, visible across the observable universe, marking the locations of the most massive black holes during their most active feeding periods. They are lighthouses powered by darkness, the most luminous objects in the cosmos fueled by the most invisible. Some supermassive black holes are dormant and silent. Not all supermassive black holes are active. In fact, most of them, in the present-day universe, are quiet. They have consumed the readily available material around them, and their accretion disks have thinned or disappeared entirely. Without fuel, they produce little or no radiation. They simply sit at the centers of their galaxies, massive and dark and patient. Sagittarius A star is one of these dormant giants. Despite having 4 million solar masses, it currently accretes very little material. Its luminosity is remarkably low, roughly 100 million times dimmer than it would be if it were actively feeding. Compared to the blazing quasars of the early universe, Sagittarius A star is practically asleep. But dormancy is not permanence. If a cloud of gas drifts too close, or if a star is disrupted by tidal forces and its debris falls inward, the black hole can awaken. These tidal disruption events, in which a star is torn apart by the black hole's gravity, have been observed in other galaxies, producing sudden flares of light that brighten and then fade over months as the stellar debris is consumed. There is something quietly poetic about a dormant black hole, an object of almost unimaginable mass and gravitational power, sitting in perfect stillness, waiting, not hunting, not consuming, just existing. The universe's most powerful objects in their natural state are also among its most patient. Some black holes have been ejected from their own galaxies. When two galaxies merge, their central, supermassive black holes eventually sink toward the center of the combined galaxy and begin to orbit each other. Over time, they spiral closer together, losing energy through gravitational radiation until they merge into a single, larger black hole. But the merger is not always symmetric. If the two black holes have different masses or different spins, the gravitational waves they emit during the final merger can be asymmetric, carrying more momentum in one direction than another. This creates a recoil, a gravitational kick that can send the newly formed black hole flying. Theoretical calculations suggest that the recoil velocity can exceed thousands of kilometers per second in extreme cases, more than enough to escape the gravitational pull of the host galaxy entirely. The black hole would be flung into intergalactic space, carrying nothing with it, leaving its galaxy behind. Observational evidence for such events is still limited, but a handful of candidates have been identified. Some galaxies show signs of having their central black hole displaced from the center. Others contain no detectable supermassive black hole at all, despite being large enough that they should have one. If these rogue black holes exist, they would be drifting through the voids between galaxies, invisible, detectable only if they happen to pass near enough to a star or gas cloud to bend its light or capture its material. They would be the loneliest objects in the universe, unanchored, unseen, traveling through the dark with nothing for company but their own gravity. Stephen Hawking showed that black holes are not truly black. In 1974, Stephen Hawking published a paper that stunned the physics community. Using a combination of quantum mechanics and general relativity, he demonstrated theoretically that black holes are not perfectly black. When they emit a faint continuous glow of radiation. This radiation, now called Hawking radiation, arises not from inside the event horizon, but from the quantum vacuum just outside it. The mechanism is rooted in one of the strangest features of quantum mechanics. The vacuum of space is not truly empty. It seethes with quantum fluctuations, pairs of virtual particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally, this process is invisible and has no lasting effect, but near the event horizon of a black hole, something remarkable can happen. A virtual particle pair can be created right at the edge, with one particle falling into the black hole and the other escaping into space. The escaping particle becomes real, carrying energy away from the black hole. And the particle that fell in effectively carries negative energy, reducing the black hole's total mass by a tiny amount. Over time, this process causes the black hole to lose mass and shrink. The radiation it emits is thermal, meaning it has a characteristic temperature. And here lies one of the great paradoxes. The smaller the black hole, the hotter it gets, and the faster it radiates. As it shrinks, it heats up, radiating more intensely, shrinking faster, in a runaway process that ends in a final burst of energy. Hawking radiation has never been directly observed. For stellar mass and supermassive black holes, the temperature is unimaginably low, far colder than the cosmic microwave background, and the radiation rate is negligibly small. But the theoretical implications are profound. Black holes are not eternal, and they are not perfectly isolated, and they carry a temperature, an entropy, and a slow but inevitable fate. The vacuum of space is not empty, and black holes prove it. The idea that empty space is truly empty is one of the most natural assumptions in physics, and one of the most wrong. Quantum field theory tells us that the vacuum is a bubbling sea of potential, filled with fleeting fluctuations in every field. Particles and antiparticles are constantly being created and destroyed, borrowing energy from the vacuum for the briefest of instants before returning it. These virtual particles are not directly observable under normal conditions. They exist for timescales so short that the uncertainty principle shields them from detection. But their effects are real and measurable. The Casimir effect, a tiny attractive force between two closely spaced metal plates in a vacuum, is a direct consequence of vacuum fluctuations. The Lamb shift, a small change in the energy levels of hydrogen atoms, is another. Near a black hole's event horizon, these fluctuations take on a new significance. The intense curvature of space-time separates virtual particle pairs that would normally annihilate. One partner falls in, the other escapes. What was a fleeting, invisible quantum process becomes a real, lasting emission of energy. In this way, black holes illuminate, quite literally, the structure of the vacuum. They are cosmic laboratories that reveal the quantum nature of empty space, turning the invisible seething of the vacuum into detectable radiation. The emptiest places in the universe, it turns out, are not empty at all, and black holes are the instruments that prove it. Black holes have a temperature, and it defies intuition. Hawking's discovery that black holes radiate energy means that they must have a temperature. And they do. But it is a temperature that behaves in the opposite way from almost everything else in nature. For most objects, adding energy makes them hotter. Heat a pot of water and its temperature rises. Feed a star more fuel and it burns brighter. But for black holes, the relationship is inverted. The more massive a black hole is, the colder it is. And the less massive it is, the hotter it becomes. A stellar mass black hole, with perhaps 10 times the mass of the Sun, has a Hawking temperature of roughly 60 billionths of a degree above absolute zero. That is colder than the cosmic microwave background, which sits at about 2.7 Kelvin. And the black hole is so cold that it actually absorbs more energy from the background radiation of the universe than it emits. In the current era, such a black hole is effectively gaining mass, not losing it. A supermassive black hole is even colder, with temperatures measured in trillionths or quadrillionths of a degree. It radiates so little that its Hawking radiation is utterly undetectable by any instrument we could conceivably build. But imagine a black hole the mass of a small mountain, perhaps a primordial black hole left over from the early universe. Such an object would have a temperature of roughly 1 billion Kelvin. It would glow with the fury of a small star, pouring energy into space. And as it radiated, it would lose mass, grow smaller, grow hotter, and radiate even more furiously in a feedback loop that would accelerate until the black hole vanished in a final burst of gamma rays. Temperature, for black holes, is a mirror image of everything we know. The smallest are the hottest, the dying are the brightest, and the most massive are the coldest, quietest, most patient objects in the cosmos. Given enough time, every black hole will evaporate. This is one of the most profound consequences of Hawking radiation. Black holes are not eternal. They have a lifespan. It is an extraordinarily long lifespan by any human measure, but it is finite. Given enough time, every black hole in the universe will radiate away all of its mass and energy and vanish completely. For a stellar mass black hole, the evaporation time is almost incomprehensibly long. A black hole with 10 solar masses would take roughly 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. The current age of the universe, 13.8 billion years, does not even register as a rounding error on that timescale. For a supermassive black hole like the one at the center of the Milky Way, the evaporation time is even longer, on the order of 10 to the power of 87 years. And for the most massive black holes known, like TON 618 or Phoenix A, the time scale stretches to roughly 10 to the power of 100 years. A googol, a number so large that writing it out in full would take more digits than there are particles in the observable universe. But eventually, after the last stars have burned out, after the last galaxies have gone dark, and after protons themselves may have decayed, and matter as we know it has dissolved, the black holes will remain. They will be the last macroscopic objects in the universe, slowly and patiently radiating their mass away, photon by photon, over time scales that dwarf everything that came before. And then, one by one, they too will fade. The last black hole in the universe will emit its final quantum of Hawking radiation and disappear, leaving behind nothing but a faintly warm patch of empty space and the laws of physics still humming quietly in the void. The information paradox is one of the deepest unsolved problems in physics. When matter falls into a black hole, it carries information with it. The quantum state of every particle, every detail about its identity, its history, its configuration, when all of it crosses the event horizon and disappears from the observable universe. According to quantum mechanics, information cannot be destroyed. It can be scrambled, rearranged, made practically inaccessible, but it must always, in principle, be recoverable. This is a fundamental law of quantum physics, as deeply rooted as the conservation of energy. But according to Hawking's original analysis, the radiation emitted by an evaporating black hole is purely thermal. It carries no information about what fell in. It is random, featureless, and entirely determined by the black hole's mass, spin, and charge. When the black hole finally evaporates completely, the information it consumed appears to be lost forever. This creates a direct contradiction between two of the most successful theories in physics. While general relativity says information falls in and is hidden, quantum mechanics says information cannot be destroyed. Hawking radiation says the black hole eventually disappears. So where does the information go? This is the black hole information paradox, and it has occupied some of the greatest minds in theoretical physics for nearly 50 years. Proposed solutions include the possibility that information is encoded in subtle correlations within the Hawking radiation, that it is stored on the event horizon, or that it leaks out through quantum entanglement. Stephen Hawking himself eventually conceded that information is probably preserved, though the exact mechanism remains unclear. The paradox matters because its resolution may hold the key to unifying general relativity and quantum mechanics, the two pillars of modern physics that have so far resisted all attempts at marriage. The answer, if it comes, may not just explain what happens inside a black hole. It may reveal the deepest structure of reality itself. The entropy of a black hole lives on its surface, not in its volume. In the early 1970s, the physicist Jacob Bekenstein proposed something radical. He suggested that black holes have entropy, a measure of the disorder or the number of possible internal configurations of a system. This was surprising because black holes from the outside seem to have very few properties: mass, spin, and charge. That is all. They appear to be the simplest objects in the universe. But Bekenstein argued that the enormous amount of information swallowed by a black hole must be accounted for somehow. He proposed that the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. Hawking's subsequent work confirmed and refined this idea. The Bekenstein-Hawking entropy formula states that the entropy of a black hole is equal to 1/4 of its event horizon area, measured in Planck units. This is an astonishing amount of entropy. A stellar mass black hole has more entropy than all the stars in the observable universe combined. But the truly revolutionary implication lies in the geometry. If all the information about a three-dimensional region of space can be encoded on a two-dimensional surface, then perhaps the universe itself works this way. This idea, known as the holographic principle, suggests that the entire three-dimensional universe may be a projection of information stored on a distant two-dimensional boundary. The holographic principle, born from the study of black hole entropy, has become one of the most active areas of research in theoretical physics. It has found support in string theory, in the ADS/CFT correspondence, and in ongoing attempts to formulate a quantum theory of gravity. And it all began with a question about what happens when matter falls into a black hole. The black hole in Interstellar was built from real physics. When Christopher Nolan set out to make the film Interstellar in 2014, he made an unusual decision for a Hollywood director. He brought in Kip Thorne, a Nobel Prize-winning theoretical physicist, as an executive producer and scientific consultant, and he insisted that the film's depictions of black holes in space-time be grounded in actual physics. Thorne and a team of visual effects artists at Double Negative developed a new rendering engine based on the actual equations of general relativity. They traced the paths of millions of light rays around a spinning black hole, accounting for gravitational lensing, Doppler shifting, and the warping of the accretion disk. The result was the first scientifically accurate visualization of a black hole ever produced for a film. The black hole in the movie, named Gargantua, is a supermassive, rapidly spinning black hole with a mass of approximately 100 million suns. Its accretion disk appears warped and asymmetric, with one side brighter than the other due to relativistic beaming. Above and below the black hole, the disk appears to arch over the shadow, an effect caused by gravitational lensing bending the far side of the disk into view. The visualizations were so detailed and so grounded in real physics that they led to 2 published scientific papers. The simulation revealed visual effects that had not been previously described in the astrophysics literature, including the detailed structure of the lensed accretion disk as seen from various angles. Art and science, for a brief moment, became the same thing. The most accurate picture of a black hole ever created came not from a telescope, but from a movie camera, guided by the equations of general relativity and the imagination of a filmmaker who insisted on truth. The time dilation in the film is genuine physics. In Interstellar, the crew visits a planet orbiting very close to Gargantua. On this planet, named Miller's Planet, time passes much more slowly than on the ship waiting in orbit farther away. 1 hour on the surface corresponds to 7 years on the distant ship. This extreme time dilation is central to the emotional drama of the film, and it is real physics. A rapidly spinning black hole, one approaching the maximum spin rate allowed by general relativity, warps space-time so severely near its event horizon that time dilation becomes extreme. Kip Thorne calculated that for the scenario depicted in the film to work, Gargantua would need to be spinning at roughly 99.8% of the maximum possible spin rate. This is an extreme, but not impossible spin. At such high spin, a planet in a stable orbit just outside the innermost stable circular orbit could indeed experience the kind of time dilation shown in the film. An observer on the planet would age normally by their own reckoning, but an observer far from the black hole would see them moving in extreme slow motion, their clocks nearly frozen. The emotional weight of this physics is what makes the film so effective. Time dilation is not just a curiosity, it has consequences. Years lost, children growing up without a parent, relationships bent by the geometry of space-time. The universe does not care about fairness. It simply curves, and time follows the curve. And the people caught in it must live with the results. Wormholes exist in the mathematics, but probably not in reality. In 1935, when Albert Einstein and Nathan Rosen published a paper describing a theoretical structure that connects 2 distant points in space-time through a bridge, a shortcut through the fabric of the universe. These structures, now called Einstein-Rosen bridges or wormholes, emerged naturally from the mathematics of general relativity. The idea is elegant. If space-time can be curved by mass and energy, then in principle it could be curved so severely that 2 separate regions of space touch, connected by a tunnel through a higher dimension. Travel through this tunnel and you could, in theory, arrive at a distant part of the universe in an instant, bypassing the vast stretches of empty space that separate galaxies. But the mathematics that allows wormholes also reveals their problems. A Schwarzschild wormhole, the simplest type, is unstable. It opens and closes so quickly that nothing, not even light, could pass through before it pinches shut. To keep a wormhole open and traversable, you would need a substance with negative energy density, sometimes called exotic matter. While quantum mechanics allows for negative energy in small temporary amounts, there is no known way to produce the quantities needed to sustain a wormhole. Most physicists regard traversable wormholes as mathematically possible, but physically unlikely. They are solutions to the equations that probably do not correspond to anything that exists in the real universe, but they remain valuable as thought experiments, tools for testing the limits of our theories and exploring what the laws of physics allow, even if nature chooses not to use them. White holes are black holes played in reverse. If you take the equations that describe a black hole and run them backward in time, you get a white hole. Where a black hole is a region that nothing can escape from, a white hole is a region that nothing can enter. Matter and light can only flow outward. Nothing from the outside universe can get in. White holes are exact solutions to Einstein's field equations, just as valid mathematically as black holes. But there is no observational evidence that they exist. No astronomical object has ever been identified as a white hole, and there are good theoretical reasons to doubt their existence. For one thing, white holes appear to violate the second law of thermodynamics. They would spontaneously emit matter and energy in an organized way, decreasing entropy, which is the opposite of what we observe in every natural process. For another, a white hole would be catastrophically unstable. Any matter approaching it from the outside would create a situation where the geometry of space-time around it would collapse, potentially transforming the white hole into a black hole. Some speculative ideas have linked white holes to the Big Bang, suggesting that the origin of our universe might be described as a white hole event, a single enormous outpouring of matter, energy, and space-time from a singularity. But this remains firmly in the realm of speculation, an intriguing idea without evidence. White holes remind us that the equations of physics are richer than reality. Not every solution corresponds to something that exists, but every solution teaches us something about the boundaries of what is possible. You cannot use a black hole to travel somewhere else. Science fiction has long imagined black holes as gateways, portals to other universes, other times, or distant parts of our own cosmos. The image is dramatic and appealing, a brave explorer diving into the darkness and emerging somewhere wondrous. But the physics does not support this. Falling into a black hole does not transport you to another location. It transports you toward a singularity, a point of infinite density where the known laws of physics cease to function. There is no door on the other side. There is no other side. The confusion often arises from the mathematical connection between black holes and wormholes. In the maximally extended Schwarzschild solution, the mathematics does describe a bridge between two regions of space-time, but this bridge is not traversable. It opens and closes faster than anything can cross it. And even if it could be held open, the interior of a real black hole, formed by the collapse of a star, does not contain a wormhole at all. It contains only a singularity, a dead end in every sense. If faster-than-light travel or interdimensional shortcuts are possible, they will not be found inside a black hole. The event horizon is not a portal. It is a boundary. And beyond it, there is only the inward curve of space-time, leading inevitably toward a point where all paths end. Black holes are the universe's ultimate recyclers. It may seem contradictory. How can an object that swallows everything and returns nothing be called a recycler? But black holes, through their accretion processes in their powerful jets, play a crucial role in redistributing matter and energy across the cosmos. When matter spirals into a black hole's accretion disk, not all of it crosses the event horizon. A significant fraction of the infalling material's energy is converted to radiation before it reaches the point of no return. This radiation heats the surrounding gas, influencing star formation in the host galaxy and beyond. In some cases, the energy output from an active black hole can suppress star formation across an entire galaxy, preventing the gas from cooling and collapsing into new stars. The relativistic jets produced by some black holes carry energy and matter across millions of light years, inflating enormous bubbles of hot gas in the intergalactic medium. These bubbles can contain as much energy as billions of supernovae. When they eventually dissipate, they enrich the intergalactic gas with energy and magnetic fields, in influencing the evolution of other galaxies. Black holes do not simply consume, they transform. They take the gravitational potential energy of infalling matter and convert it into radiation, jets, and kinetic energy that reshape their surroundings on scales far larger than themselves. They are engines of cosmic change, turning the quiet infall of gas into some of the most powerful phenomena in the universe. In a way, black holes are the universe's foundries. They take raw material, process it through the most extreme conditions possible, and send the products back out into the cosmos, changed and redistributed, ready to become part of the next generation of stars, planets, and perhaps, eventually, life. The quietest objects in the universe. A black hole that is not actively feeding is one of the most silent, most still objects imaginable. It produces no light. It emits no sound. It generates no heat that any instrument could detect. It simply exists, a region of curved space-time, patient and unchanging, waiting for something to wander too close. Sagittarius A star, the supermassive black hole at the center of our galaxy, is in this state right now. Despite having 4 million times the mass of the Sun, it is remarkably quiet. Its luminosity is a tiny fraction of what it could produce if it were actively accreting. The stars around it orbit peacefully. The gas nearby drifts slowly. The black hole makes no demands. It simply sits, and the galaxy slowly turns around it. There is a strange kind of peace in this image. The most gravitationally powerful object in the galaxy, and it is doing nothing, not consuming, not radiating, not growing, with just being. A point of absolute calm at the center of a spiral of 200 billion stars. In a universe full of activity, full of explosions and collisions, and the constant churn of matter and energy, a dormant black hole is an island of stillness. It is the universe holding its breath, quietly, indefinitely, with no reason to exhale. Black holes preserve something we may never access. Every particle that has ever crossed an event horizon carries information. The quantum state of every atom, every photon, every bit of energy that falls in is added to the black hole's total information content. The event horizon grows, the entropy increases, and the information is sealed away beyond the reach of any observation. We do not know what form this information takes inside the black hole. We do not know if it is preserved in any meaningful structure or if it is scrambled beyond recognition. The information paradox tells us that the information is not destroyed, but it also tells us that we cannot access it by any known means. In a way, a black hole is the universe's most secure archive. Everything it has ever absorbed is recorded somewhere, in the correlations of Hawking radiation, in the quantum state of the event horizon, in some encoding that our current theories can only hint at. Nothing is truly lost. It is simply hidden, locked away behind a door that opens only inward. There is something quietly reassuring about this. In a universe where entropy increases and disorder grows, where everything tends toward dispersal and decay, the black hole stands as a counterpoint. It gathers, it preserves, it holds. Not forever. Eventually even black holes fade, but for time scales so long that the word forever feels almost appropriate. Darkness is not always emptiness. We often associate darkness with absence. A dark room is an empty room. A dark sky is a sky with nothing in it. Darkness means nothing is there. But black holes teach us that this intuition is wrong. A black hole is the darkest object in the universe. It emits no light. It reflects no light. It is as dark as anything can possibly be. And yet, it is not empty. A supermassive black hole contains more mass than millions or billions of suns. It warps space-time so severely that it alters the paths of stars and galaxies around it. It anchors the structure of its host galaxy. It is among the most substantial objects in existence. Darkness, in the case of a black hole, is not absence. It is presence. The most concentrated presence the universe can produce. The darkness of a black hole is not a void. It is a fullness so extreme that nothing can escape it, not even the light that would make it visible. Tonight, as you rest in darkness, perhaps this thought offers a gentle comfort. The darkness around you is not empty. It is filled with air, with warmth, with the quiet sound of your own breathing. It is the condition under which your body heals, your mind rests, and your memories consolidate. Darkness is not something to fear. It is something to settle into, like a black hole settles into the center of its galaxy, still and full and patient. The universe is not afraid of its own black holes. If black holes were truly the monsters of popular imagination, the universe would be a very different place. Galaxies would be torn apart. Stars would be dragged screaming into oblivion. Space itself would be unsafe. But the reality is far more peaceful. Galaxies coexist with their central black holes in a relationship that resembles symbiosis more than predation. Stars orbit supermassive black holes at the centers of galaxies for millions of years without incident. Gas clouds drift past at safe distances. Planets form and life evolves in galaxies that harbor black holes of staggering mass. The Milky Way has had a 4 million solar mass black hole at its center for billions of years. And here we are. Earth orbits the Sun 26,000 light-years from the galactic center, untroubled by the quiet giant in the middle. The black hole is there. It has always been there. And life has flourished around it, not despite it, but indifferent to it, separated by distances so vast that its gravity is imperceptible. Black holes are not enemies of life. They are features of the landscape, like mountains or oceans, enormous and powerful but not hostile. The universe has made room for both black holes and butterflies, for both singularities and sunsets. They coexist, each following the laws of physics, each playing a role in the vast, quiet ecology of the cosmos. Even black holes will eventually fade. Nothing in the universe is truly permanent. Stars burn out, galaxies disperse, protons may eventually decay, and black holes, the longest-lived objects the cosmos will ever produce, will also, in the fullness of time, cease to exist. Hawking radiation, faint and patient beyond all human measure, will slowly drain every black hole of its mass. For the supermassive black holes at the centers of galaxies, this process will take 10 to the power of 100 years, a timescale so long that it makes the current age of the universe seem like the first instant of a very long morning. But the process is inexorable. As each photon of Hawking radiation escapes, the black hole loses a tiny amount of mass. It shrinks, its temperature rises, its radiation rate increases. And eventually, after all the stars have died, after all the matter has decayed, after the universe has grown cold and dark and still, the last black hole will emit its final photon and disappear. What remains is not nothing. The energy that was the black hole has been returned to the universe, photon by photon, spread thinly across an incomprehensibly vast and empty cosmos. The black hole has given back everything it ever took, just very, very slowly. There is a strange gentleness in this ending. The most fearsome objects in the universe do not die in violence. They fade, quietly, patiently, like a candle in a room where no wind blows, burning down so slowly that you cannot tell, from one moment to the next, that it has changed at all. And when it finally goes out, the darkness it leaves behind is the same darkness that was always there, warm and full and undisturbed. And now let the mystery of black holes gently fade into quiet wonder. We have traveled far tonight. We began at the edge where light still escapes and moves slowly inward, past the event horizon, past the photon sphere, toward the singularity where all known physics falls silent. We learned that black holes are not holes but objects, not vacuums but anchors, not destroyers but transformers. We watched massive stars collapse in supernovae, their cores crushed beyond the limits of matter. We stood at the event horizon and realized that crossing it would feel like nothing at all, even as it sealed our fate. We saw time slow to a crawl, space twist and drag, and light bend into circles around a darkness so deep that it warps the geometry of the universe itself. We met the silent giant at the center of our own galaxy, orbited by stars that trace its invisible shape with their faithful movements. We saw the first photograph of a black hole shadow, a ring of fire around a circle of absolute darkness, confirming equations written a century ago by a man who could only imagine what we can now see. We followed Hawking into the quantum vacuum and learned that even black holes are not truly black. They glow, faintly, patiently, and they will one day fade completely, returning everything they ever consumed to the universe that made them. Through all of this, a quiet truth kept surfacing. Black holes are not something to fear. They are something to wonder at. They are the universe's most extreme expressions of gravity, of geometry, of the relationship between matter and space-time. They are places where our deepest theories are tested and our deepest questions remain unanswered. And yet, for all their strangeness, they follow the same laws that hold you gently to your bed tonight. The gravity that bends light around a black hole is the same gravity that keeps the moon in orbit, that holds the atmosphere against the earth, that pulls your blanket softly against your body. It is the same force expressed at different scales, and it is everywhere, always without exception. Tonight, the darkness around you is not a void. It is a presence. It is full of air, full of warmth, full of the quiet hum of a world at rest. And somewhere, 26,000 light-years away, a supermassive black hole sits at the center of your galaxy, still and silent and patient, while 200 billion stars turn slowly around it. You are part of that turning. You are made of the same atoms that were scattered by the supernovae that created the black holes you learned about tonight. You are held by the same gravity. You are woven into the same space-time. And right now in this moment, you are resting, which is exactly what the universe, in its quieter moments, seems to do. So let the questions settle. Let the darkness feel soft. Let your thoughts grow dim and gentle, like the last photon of Hawking radiation drifting away from a black hole that has finally, after an eternity of patience, found its peace. Sleep well. Even in the deepest dark, something endures. Good night.